Hello, I am thrilled to introduce Ben-Sasson, I'm sure all of you know, perhaps from him co-founding Starkware and being the current president, or from him co-founding Zcash, and also currently serving as a professor in computer science at the Israel Institute of Technology. He's going to share with us a presentation, and then we'll have some Q&A. I'm really pleased to pass over. Thank you.
Thank you, Tom. So I want to tell you a little bit about StarkNet and how we got here. So, the first thing I want to tell you is that StarkNet is open for business, for developers. There's a thriving ecosystem, and I invite you all to join. A good place to start your journey is on the Discord server, which can be found using this QR code. So, where should I point this? Okay. There's dozens of projects already deployed and a lot of fun, a very thriving ecosystem. And to quote one of the developers there, one of the leading developers there, Itamar Le Suisse, CEO of Argent, saying, StarkNet's ecosystem feels like early Ethereum. It attracts the best talent in the space with its decentralized approach to development and innovation. And here's another thing, just from last week. Which way should I point it? What? Sorry. Just one second. So Moody Salem is one of the core developers of the Uniswap project, and here's what he just tweeted a few days ago, that he's basically leaving the Uniswap team and embarking on StarkNet. He says, I'm a big believer in the ecosystem, in Cairo 1.0, StarkNet, next version, which has been called by the community more TPS Daddy. And they are a huge leap forward and will finally make ZK proofs accessible to normie developers like me. He's starting work on an AMM that will use these capabilities. So these are just examples from the past few days or weeks about the way the community is viewing StarkNet. So basic thing is invitation for you to join. There are more than 1,000 GitHub repositories in the programming language, the new one called Cairo, the one that we invented for the purpose of making Ethereum scalable. And it's a thriving ecosystem. Please join us. Now I want to tell you how we got here. And this is a story that starts with math, and it actually is a story about integrity through math. And there's a definition of integrity that was given by an Oxford alumni by the name of C.S. Lewis, the famous novelist and author. And he defined integrity as doing the right thing even when no one is watching. And Stark is a technology that uses math in order to know that the right thing is being done even when you're not watching. Now, this goes back something like 3 to 4 decades ago in the math and computer science literature. Here's a beautiful quote from a very influential paper from 1992 that already prophesizes about the technology that now StarkNet is using. And I'm reading this quote from a paper by 4 brilliant mathematicians, Lassi Babai, Lance Fortnow, Mario Segedi, and Leonid Levin. And it says, this technology allows a single reliable PC to monitor the operation of a herd of supercomputers with powerful but unreliable software and untested hardware. So this is a prophecy made in 1992 about how you can use math in order to ascertain integrity of computers that are running outside your view and still know that the right thing is being done even when you're not watching. So I want to give you a little taste for what this technology looks like. And what it does is it enforces integrity on computations that are done outside of your view. So let's take an example of a claim that we would like to know has been computed or processed with integrity. So someone is claiming that starting from a certain state of the system represented by a hash X, that person has processed 1 million transactions. You don't know the details of these transactions, but at the end of this processing, the new state of the system is the state Y. Now, of course, if these transactions represent a lot of value, as they do on a blockchain, you might worry whether this person who has been processing them is operating with integrity. Is he really doing the right thing? Is he really working in accordance with the program P? Okay? So the way math comes in is that there is a mathematical way to convert such a claim, basically take the 4 parameters of this claim, which are the starting state X, the end state Y, the number of transactions, and the program that has been used to process them. And from these 4 parameters, create, via something called a reduction, create a sort of a puzzle, a Sudoku-like puzzle. And the way this technology works is that in order to convince you that the claim was executed with integrity and the claim is correct, the prover, the person or the entity who is making this claim, should submit a solution to this puzzle. These are the red numbers there. And then what you do using this technology, again, that was already prophesized in the 1980s and early 19s, is then you go and sample one small local constraint out of the many constraints that are supposed to be satisfied in the puzzle, and you just examine it. Now, if the number patterns there satisfy the constraint or the definition of what should happen in that little part of the Sudoku-like puzzle, then you accept the claim is correct. And otherwise, you say that you're not satisfied. So this is known as the PCP theorem. It's a very famous theorem from the 1990s in theoretical computer science that has profound implications. And here's where the magic lies. So it turns out that first of all, when the verifier comes to sample and examine, these like 3 numbers, that verifier does not need to write down the whole puzzle. There's an efficient method that just using random coins with very efficient running time, the verifier can know which entries to read and what to check when she read these entries. So that's where efficiency and succinctness come from. The second magical property is that if the claim is correct and has been computed with integrity, then there's an efficient algorithm that will fill in the red numbers in a way that all constraints are satisfied. We call this perfect completeness. And the last and most important and hardest to prove mathematical property is that if the statement is false, then no matter how the number patterns are filled in, at most 1% of the constraints will be satisfied, which means that if we sample, let's say, 3 random constraints and check them, the probability of erroneously accepting a falsity goes down to 1 in a million. And if we repeat this, let's say, 20 or 30 times, the probability that we accept a false statement as correct is smaller than the probability that, as we're speaking now, a meteorite, strikes this place and eliminates all life on Earth. It's a very small probability. So from a practical point of view, if we sample such constraints and check them, we have a near certainty or practically good certainty that we are not being fooled. So we have here this magic concept or this magic construction that uses math in order to quickly and efficiently ascertain the integrity of a vast amount of computation, much, much larger than the amount of computation that is being done in order to verify it. And what a Stark is, it's a improvement on this technology in which what we do, instead of asking the prover to submit one solution, we repeat this sort of puzzle and solution process a number of times. After the first solution has been submitted, we ask for another solution, for another puzzle, and then it is filled in, and then we ask for another puzzle, and at the very end, we sample one constraint across this sort of 3-dimensional or multi-dimensional Sudoku-like game. And Before being an entrepreneur in blockchain, I was purely a mathematician and theoretician. And I can summarize my 15 years of research in that area. At chiseling, I could summarize it as saying that what I did was try to chisel away and remove 2 letters from this slide. So the initial constructions from the 1980s and 1990s were asymptotically efficient, but not practically so. There weren't enough atoms in the solar system in order to write down solutions for one of these Sudoku-like challenges. And what my collaborators, my students, my peers, and I did over these 15 years was come up with better and improved mathematical protocols that will make it more efficient, so that now we have enough atoms, not just in the solar system, but actually on computers like laptops and on the cloud in order to make this thing a reality. So this brings us to the question. So now we have the math and the technology to make this work. So now we have the math and the technology to make this work, but what was missing is the use case. Where should we apply this marvelous technology that lets a very weak computer ascertain the integrity over a larger computation? And this is where blockchains come in, because in the world of blockchains, we have these systems that you could think of as very trusted computers, but very slow ones. If you think of Ethereum, it has the ability to execute any computation, to run any smart contract, but it is very slow compared to the demand for Ethereum's computation. So as a weak computer, and we would like, but one that we trust very much, and we would like to use it in order to bring integrity or ascertain integrity over vaster amounts of computation. So this ability to use the math that was envisioned in the 1980s and 1990s in a practical use case that is very important is exactly this merging of proofs. Sometimes they're called ZK proofs or validity proofs, this merging of them with blockchains. And I'm proud to say that or lucky to say that I was probably the first to notice this connection between general purpose cryptographic proofs and blockchains. And it dawned on me in a conference on Bitcoin in 2013, more than 10 years ago. It was in May 2013. I gave a presentation on my academic and practical work, and I presented how you can use both the privacy and the scalability of things like Starks and Snarks and other such cryptographic protocols in order to improve the scalability and also the privacy of blockchains. So this led to Zcash. I was one of the co-founders of it. It's the first use case of general purpose zero-knowledge proofs in order to preserve privacy of blockchains. And 3 years later, I co-founded Starkware, which is the first use of validity proofs and Starks to scale blockchains. And now we're 5 years later, everyone's talking about scaling blockchains with validity proofs, but I can tell you that 5 years ago we were the only ones saying that this is the way to go, and a lot of people didn't, didn't think that scalability is a problem, and they certainly didn't think that the best way to solve it is with Starks. But now I think the world has, come to agree with this. So now I want to address a little bit the title of my talk and explain why I think Starknet really is the ultimate end game for integrity webs. So a little bit of I guess my theoretical background likes to, pushes me towards trying to define things properly. So I'll start with a quote of integrity. Again, the Oxfordian C.S. Lewis gave a beautiful definition. Integrity means doing the right thing even when no one is watching. And when we think about money or things like that, we know what the right thing is. We know that, money shouldn't leave one person and move to another without the agreement of others. and so on and so forth. So I have 10 minutes. So we have 10 minutes, including Q&A, right? Okay. So I won't speak about this. We'll move to the Q&A. Let me just say that StarkNet, with its ability to expand dramatically the scale of blockchains, in particular Ethereum, and do so even recursively with things like layer 3 and standalone systems, is really what's going to bring massive scale to the global demand that exists today for blockchains, which I'll share the slides and you can share them onwards. So Tom, back to you if you want to ask questions.
Thank you very much. I'll start with something related so you can almost finish off and answer a question at the same time. Given the superior privacy and scalability of Stark versus, say, the EVM, how do you go about getting the application layer, even if you have the superior technology?
So I think what happens, and we see this often with technology and programming languages and frameworks, is that there's some prevailing system or framework that everyone might be using, and then some newer technology comes along, and this happens all the time. And then what you see is that, well, there's this process by which a few early adopters, first of all, they move to the new technology, to the new and better technology. The vast majority initially stay with the older technology. Over time, some of them port more and more so. But in the end, there's some mixture of both. And if you think about, let's say, programming languages, so, COBOL versus C versus Pascal or Rust and Python, you see similar processes happening. So I think what's going to happen with things like StarkNet and its new and improved programming language is called Cairo, is that some developers are going to jump ship and move to it. Others are going to stay working over Solidity and Ethereum. And in the long run, we will see some mixture of both of these and probably newer languages that are going to be even better than what we see today.
Sure, that's useful, thank you. And a question relevant for a large proportion of our university audience today, in terms of balancing academic versus entrepreneurship. Where do you think at the moment that balance lies, and where do you think it should lie as a student?
Yeah, so as someone who started off as a pure theoretician and now has morphed into a very practical entrepreneur, I would say, first of all, that both of them are needed and should be loved and given their own space, meaning I think scientific exploration and research are at their best when scientists are given freedom to do whatever they want. And then most of them are probably going to be very happy just staying in the labs and doing the research or, by the whiteboards, which is fine. One thing that, at least my own experience, was a bit suboptimal, at least in the academic institution that I was at the time, was that sometimes academic institutions, they give freedom to researchers when they're doing research, but if those researchers try to do entrepreneurship, then they find it a bit harder. Suddenly the institution wants to have a very large piece of it or to dictate the terms for it. And I think that's not the way to go. I don't know how it is in the UK. I actually heard good things about UK universities and their approach to commercialization. Certainly in the US, it's working very well. So I think as long as the researchers are given the freedom to explore what they want, including if it's within the realm of entrepreneurship, that's probably the best thing for society.
And in one of the talks earlier, this actually came up, and Ellie walked in and answered a question exactly as he arrived. It was brilliant, and I want to ask a similar question again, which is around the quantum resilience of Stark relative to other protocols.
Yes, so there are out there a very large number of cryptographic protocols, different ways to get integrity and to get privacy. They have very many funky names. There are, of course, Starks, there are Snarks, there are Plonks, there's Halo, there's a very large number of protocols. And I actually wrote a blog post titled The Cambrian Explosion of Cryptographic Proofs. Now, the question is about post-quantum security. So many of these constructions, the way they work is they use a lot of structure from number theory, and in particular they use cryptographic assumptions that are either directly related or implied by things like the hardness of prime factorization. So how hard is it to factor a composite number into its prime subcomponents? And some of these constructions that are often called snarks, but not just, they rely on these assumptions and they rely on the hardness of factoring numbers. Now, quantum computers, if they ever exist at scale, factor integers very well, exceedingly well. That's probably the most famous thing that quantum computers do and that we don't know yet how to emulate on classical non-quantum computers. So that's why a lot of the constructions that are under the family known as snarks will be broken by quantum computers. There are other problems there related to trusted setup, the ability of, even without quantum computers, the ability of a malicious party to bake the system and insert a trapdoor of sorts that allows it to submit false proofs. Now, the nice thing about Starks is that, and the constructions that we use inside StarkNet, is that they rely to a very large degree on math that does not rely on any cryptographic assumptions, meaning that even if there is a computationally unbounded adversary that has not just quantum computation, efficient one in its hands, but even vastly more, if it can compute things like, you know, computations that are greater than the number of atoms in the visible universe per second, the math of Starks still is immune against such adversaries. There's only one aspect in which we need cryptography, and it's a very minor one, and that is we need what is known as a collision-resistant hash function. So because of the very minimal reliance on cryptography and very safe cryptography, there are a lot of constructions of collision-resistant hash functions that are immune to quantum computers, at least according to our understanding today. And that's why Starks are post-quantum secure.
And having time for one last question. In the future, what do you think the network of validators and provers will look like? And how do you think it will change in the current landscape?
So it's a terrific question. Those who are familiar with the way blockchains work today, well, and this relates to this notion of integrity web, we really have this very large web of computers that are validators, and each and every one of them is re-executing the same computations that others are doing, right? And it's a very secure process, but it is also extremely inefficient, especially if you want your network to be very broad and maximally broad and allow everyone with their laptops and smartphones to participate in this beautiful web of integrity, right? So there's a tension between the broadness of a blockchain or an integrity web and its scale. Now, what is nice about Starks and proving technology in general is that all we need in order to advance the system is one party that is willing to generate a proof, and we need no trust assumptions about the integrity of that party because the proof takes care of that. So what I think we'll see in the future is we'll see an even broader set of validators that each of them is performing very, very simple computations that are mostly about verifying Starks. And then we will have a large system, an ecosystem of separate provers, each one of them taking care of separate aspects of the ecosystem. You know, one is processing payments in the Oxford area. Another one is processing payments in some other county in the UK. And then there's another where there's a game being played, and so on and so forth. And the nice thing is that we don't need trust assumptions between these different provers. Each one of them will generate a proof for its own batch of computation, and these proofs are very efficient to verify and ascertain integrity over. So summing up, in the future, we'll have this ecosystem where you'll have a lot of separate proving capacity separately, done on different machines. And it's all brought together inside this beautiful and very performant and scalable integrity web by allowing weak computers to ascertain the integrity of bigger computers out there. And this was, again, goes back to this prophecy already made in 1992, where you have a weak computer, but one that is very trusted, that now can harness the integrity and control and ascertain integrity over a vastly greater amount of computation.